So now we can use this concept to something a little bit more complicated. So we'll talk now about logistic regression. And logistic regression is a model that allows us to classify objects. So for instance, if we take a spam detector, the simplest possible spam detector, I think, or one of the simplest spam detectors. So we can, for instance, express a message as a set of binary random variables, for instance, whether a word occurs or not. Then, of course, our decision is whether this is a spam or not. And the goal is to provide probability of a spam or in general to classify messages, right? How we can formulate it? Now we will use our good fellow Bernoulli, and we will represent it as a Bernoulli distribution. And in the Bernoulli distribution, we have this probability of spam or not, right? So this is the variable y. Now the variable x denotes the sequence of words in this case, right? And now we have also something new here, two new things. So first new thing is this theta. So this is a set of weights, we can call it. And we have something like sigma, right? So this is sigmoid function. And why we use that, right? So please think about this Bernoulli distribution, or where we talked about this tossing a coin. So think of this coin that actually it will behave differently because, for instance, different hand will toss it. And now this hand is our, so the probability of head and tail is dependent on a hand, okay? And now this hand is, in this case, a message, and coin is spam or not. And we say that the dependency between message and spam or not is linear. So there is this linear dependency with this weights theta. And why sigmoid? Because we need that we model now probability of being a spam or not. So it must be between 0 and 1. And sigmoid function is very useful for that, because this is a function that squashes real values to values between 0 and 1. So this is exactly what we want. So this is what we call the logistic regression, okay? So further, we have very nice properties of the sigmoid function, and the first nice property is that the derivative of sigmoid function with respect to the input is just expressed again using sigmoid function, so it's sigmoid times 1 minus sigmoid. And also that sigmoid of a negative value inside, it's just 1 minus sigmoid function. So and this is this anti-symmetry in some sense. And in our model, we have that probability of getting a spam. It's simply sigmoid of this linear dependency of messages, words in message. And probability of not spam or ham, it's actually 1 minus this sigmoid. So everything now should get together nicely. And again, if you don't follow it, just pause, look at slides, think about it 2 times or 3 times, and it should become clearer and clearer. Now we can even express it as some kind of very, very simple network, okay? But for now, without any hidden layers. I think that now you should see where we are heading to, and we'll use this fact in a second. Before that, of course, we should think of learning algorithm, and in this case, because we have some now nonlinearity, and sigmoid function is nonlinear, so we will use gradient descent, and for that we need to calculate the gradient, so a vector of derivatives, first order derivatives of the the negative log likelihood, right? We assume that our data are IID and we can change the product into the sum. So first, of course, we write down what is the Bernoulli distribution in this case. So you see, we change the probability, we express it as sigmoid of this linear dependency. We also use the fact that 1 minus sigmoid is just sigmoid of minus inside of the negative argument. So we can further go with the gradient inside. And why? Because the gradient of a sum is sum of gradients. So we use this fact. We apply here these properties of sigmoid function. Now we see that we can start actually canceling some elements. We can simplify it, and we can further simplify it. We can calculate multiply by y or 1 minus y and reorganize it to end up with a very nice gradient. So now we say that the gradient of the negative log likelihood function is simply a sum over all possible observations, where our model simply takes the difference between our prediction, so sigmoid, minus difference between sigmoid and the label, right, times x. What does it mean? It means that if we are correct, if our model is correct, the weights of this, so theta, will be not changed, because if the sigmoid is almost 1 and the label is 1, then we will have 0. But when the mismatch is huge, so for instance, our model predicts almost 0 and the label is 1, we will follow the direction, so minus 1, direction of x. And this is how we'll update our weights. So the update rule of the gradient descent is, of course, also multiplied by some alpha factor, right? So this is so-called learning rule. But what if the number of messages in this case, or in general, the number of observations is really large? So then we should use something which is called stochastic gradient descent. And stochastic gradient descent tells us that use just simply mini batches. In the most extreme case, we just take one single example and we follow this and we just update immediately. I will not go into details of stochastic gradient descent, but there is a lot of beautiful works about this, papers about this algorithm, and you can maybe take a look at them, Google a little bit if you want to understand it more. For our purposes, gradient descent, mini batches, stochastic gradient descent, this is what we will use extensively, and this is what is a standard thing to use in deep learning. To see how, to have a feeling how these two models work, these two algorithms work. So stochastic gradient descent, if the goal is to to get to this big dot in the middle, it will just make a little bit like random moves, and not necessarily super straight to the point, but something like a little bit left, a little bit off, a little bit back to the left or right, off again. But in general, it will converge. And since we don't need to look at all data points at once, but some small chunks of data, it turns out that actually this sometimes converges even faster than the full gradient descent, or batch gradient descent, full batch gradient descent, however we call it. Because then you need to solve this big sum, you need to calculate, bam, I have an update, I move. Again, you calculate a lot, you use a lot of memory, and you move again. Of course, the standard issue, especially with deep learning, we need to keep a lot of weights. So we have some limited memory. So that's why stochastic gradient descent, you take some small chunks, small batches of your original data. At the end of this lecture, I want to make a quick introduction to fully connected neural networks. And we do it immediately now because there is a very nice way of looking at fully connected networks as stacked logistic regressors. Okay, so the question is, of course, yeah, what if we stack multiple logistic regressors now? So this showing this slide before where we have this small network, right, was of course on purpose, and I'm sure that a lot of you already predicted what is going to happen, that we will now stack them together, right? And so this is what, of course, we do, and of course, what we can do. And then right now, we will just say that, hey, between our original input and between and the output, input and output, we can put logistic regressors. Okay, so every single this logistic regression in the middle will have own set of parameters or weights. This is denoted by bold W. Of course, the number of these hidden nodes inside, or these nodes inside, is typically lower than the number of inputs. So this is denoted by M. And then in the end, we have, again, if we forget about X's and W and focus on H, we can say that, again, we have on top of that a logistic regression. So this is really like combining a lot of logistic regressors together. And so how does it look like? So if we write again the probability of a ham or whatever else, something like a coin or something. So this is again the Bernoulli distribution. So we need sigmoid. And then simply now we replace our x with some kind of transformation, and we can call it like new variable h, right? And this is again this sigmoid of w times x. So as you see, now we have something like stacking these probabilities together. But in the end, we are interested in predicting this probability of y, not something else, right? So again, we just will use the log likelihood function as our objective, because we can do that. It's again Bernoulli of y for given probability. And this probability is now just more complicated function, but still returning values between 0 and 1. This h is h and not k or whatever, because it is a hidden layer. This is how we'll call it, and one single node inside will be just called neuron, okay? Or as Rosenblatt called it, the perceptron, if there is this step function instead of sigmoid. And of course, we can stack even more. There is nothing that stops us from that, right? We can stack 100. And now you get why we call it deep neural networks, because we have very deep dependencies. So this is how we have the model, how we can construct fully connected neural networks, just by imagining that we just have a lot of these logistic regressors, and how we can actually interpret this one single neuron somewhere inside this network. This is our feature extractor. And especially this is apparent if you think about sigmoid functions. So you can say that this is, in some sense, this is like, what is the probability that given feature occurs here? Okay, so this is how we can think of this representation learning and these multiple levels of abstractions inside. And why abstractions? Because we have this weight. So if I take one neuron and it is dependent on everything before, on some other neurons, for instance, first they detect some edges. So now this neuron tells me, all right, I should take this feature, this feature, this feature, this feature with very specific weights and combine them together, okay? And then this will say, all right, so the probability of this feature, this combination of these things below, is, for instance, 0.7, but probability, right? So this is not probability. Only the last layer predicts the whole probability of this whole thing, right? So now what are components of fully connected networks? First of all, we distinguish something which is called a linear layer. So this is just, again, a linear combination So we take input, we calculate, multiply it by a matrix or a tensor, but here a matrix, and this is linear layering. Sometimes we can explicitly add a bias to that to be sure that that we are aware that we can actually shift it, right? So affine transformations. For simplicity, we will remove this bias B, but please keep it in mind that it is there. Then we have some kind of nonlinearity, right? So some function. We told about the sigmoid function, but of course we can have different types. Only the last layer has to be sigmoid because we want to have values between 0 and 1. But there's nothing against to use something else. And this is actually also a reason why deep learning became so powerful, because at some point someone realized that, hey, we can use something different than sigmoid. And why not sigmoid? You will see in a second. But what we can use instead of sigmoid, we can use tanh, another sigmoidal function, but now for values between -1 and 1. We can use ReLU, something that is super common right now. Basically, most of architectures, they use some kind of ReLU function. And what is ReLU? It is for negative values, it returns 0, and for positive values, it returns linear function. So very specific kind of very peculiar nonlinearity. So it's like 0 and then it's 1. A linear function. When we have a linear layer, this is extremely important to initialize it properly. So in other words, how we initialize it before seeing any data. So how we initialize these feature extractors. So we can use simply Gaussian with some variance. It should be around 0, not to bias it towards something. So we have 0 and some small variance that these values are around 0, a bit negative, a bit of positive. For tanh, there is a specific value for variance where there is this square root of 1 divided by the number of inputs. And for ReLU, it is 2 divided by number of inputs. There are some analysis that provides motivation for this kind of initializations. Okay, so these are the most commonly used initializers. Also, to see how these activation functions work. So again, we have sigmoid, tanh, and ReLU, and below there are gradients, right, of them. And as you can see, the difference between sigmoid and tanh lies only in having this scale is a little bit different, but shapes are the same. But for ReLU, we have a step function that is very, very interesting, right? So it is something like either we have a gradient or we don't have a gradient. And this is something that is called sparsification. And some people claimed, including Joshua Bengio back in the day, that this is extremely important for deep learning to somehow have this sparsified neural network, that some weights are getting, or some outputs are getting 0. All right, so far we talked about 2 classes, right? So we use sigmoid for modeling probabilities. So what about K classes? So for so-called categorical distribution, right? Of course, we can use neural networks for that as well. And the only difference is that we need to output the softmax function. So we need to have now for each class a separate set of weights. And we said that neural networks are stacked logistic regressions, right? So now the question is, can we use the same ideas, the same learning algorithms as for logistic regression? Can we use SGD? And the answer is, of course, yes, we can. But now we need to be a little bit more careful because it will be not so easy to calculate gradients by hand. But we can do it. So let's consider this one hidden layer in neural network. So we have one hidden layer with some nonlinearity f inside. What we can do with that? Because now we need to calculate gradient with respect to w and theta. We can use the chain rule to calculate these gradients. Okay, now we just what is the chain rule? it tells us that if we are interested in calculating gradient or derivative with respect to u of some function L, like loss function, so then we can just simply introduce some intermediary derivatives, all right? And in our case, this is the negative log likelihood. We calculate gradient with respect to some weights u, and then we actually follow, right? And this is the thing of the idea behind backpropagation algorithm, right? That we can actually build these derivatives by having modules in our neural network. So one layer, second layer, and so on, so on. Of course, for full derivation, you can do it as a homework for this hidden layer, one hidden layer neural network, or you can wait till the next lecture when Peter will do it for you. Right. There's another thing that is worth to mention at this point is that the sigmoid function is a good choice to model probabilities, so at the end, but it's very bad idea to use it for hidden layers. Actually, this was a reason why neural networks were not so successful in the end. In 90s, people used no more than 3 layers, and they thought that, well, these models can't learn anything else. But later on, people realized that actually the reason for having shallow neural networks is that there's the problem of vanishing gradients. And what does it mean? It means that if we calculate gradients of sigmoid function, we get this sigmoid times 1 minus sigmoid. And when our model is very sure about something, and the sigmoid is close to 1, what happens? We get the gradient equals 0. And what does it mean? If we calculate, we propagate, let's say, from input to output, and at some point in the middle, we'll get values that are close to 1, and we backpropagate. So we go to output and we backpropagate. So suddenly, our gradient will zero out, and we will not update these first layers. Okay? So layers close to input will be almost unchanged and almost like random. So this was the problem. The larger the network, the further from the output, layers further from the output, they were almost like random. And this was something like people thought, okay, 3 layers is no more we can do, only 3 layers. And to see it even better, so we have this that in the middle, what I explained using hands. So this is more formal. So just in the middle, we can have something that will zero out, and eventually we'll have no update. And that's it for the first lecture. Okay. I think that I introduced everything. Please visit Canvas page. We'll provide all information there. If there is something unclear, please let me know. I forgot to mention that our original time slots for lectures we'll use for Q&A sessions, okay, where you can ask questions. But of course, for each Q&A session, you have to watch these lectures, because we will not go through these slides. We will just answer your questions, something that is unclear. Okay, so thank you very much. It's really pity that we cannot see each other in real life, but well, this is what we have to deal with. It will not stop you from learning super cool ideas about deep learning, and I'm sure even that you will enjoy our assignments, even though they are maybe very challenging and hard. But that's the point, right? You want to learn something, and the best way of learning is to just working hard. Okay, so thank you very much, and see you next time.